In this example, we want to determine the equations for the reflected and transmitted portions of the E field when we have an incident TEM wave that moves from air into some new media, and the incident electric field vector is given as having a pointing a little bit in the x direction and a little bit in the y direction. So notice that it doesn't point in the z direction, so that means that the E field is still perpendicular to the impedance boundary here. So the first thing that we need to do is we need to convert this over into phasor form. So that's going to be E bar incident is going to be equal to the initial amplitude 40. We need to convert this to its phasor form, so that's just e to the minus j beta 1z. There was no attenuation here. And then there's a second, and that's pointing the a hat x direction. And then there's a second component, e to the minus j beta 1z. How do we handle this phase shift? It's e to the j pi 4. Sorry, that's e to the j pi over 4. And that was pointing in the a hat y direction. So now we've converted this over into the phasor form. The first media was air, so N1 equals N air, which is just for a vacuum, 120 pi ohms. We need to know the eta for media 2, and we can use the relationship that N2 is equal to intrinsic impedance of free space times the relative magnetic permeability of media to the relative electric permittivity of the media. So for media 2, this is going to be 120 pi times the root of 2 divided by 12. And so that is 1/6, that's root 6, root of 1/6, and we multiply that all out together and we get 48.99 pi ohms as the intrinsic impedance of media 2. I can now determine the reflection coefficient for the TEM mode and the transmission coefficient for the TEM mode just by using the formula eta 2 minus eta 1 over eta 2 plus eta 1, and so that's going to be 48.99 pi minus 120 pi over 48.99 pi plus 120 pi. And that gives me a reflection coefficient of minus 0.412. And the transmission coefficient, I think, is most easily calculated by just adding 1 plus the reflection coefficient. And so 1 plus minus 0.412 is equal to 0.588. I can then determine the magnitude of the reflected wave ES to the R. That's equal to the reflection coefficient for the TEM mode times the magnitude and phase of the incident wave, and so that's going to be equal to minus 0.412 times the magnitude, which was 40 here, and then the second magnitude was 4. So it's got two components. This is the a hat, that's the component in the a hat x direction. This is the component in the a hat y direction. So this is going to be minus 16.48, and this is going to be minus 1.648. So I can now write ES R. Oh, sorry, that's E0 of R. That's not ES of R. ES of R is equal to minus 16.48, that's the initial amplitude I determined here, e to the j beta 1z, that's in the a hat x direction, minus 1.648 e to the j beta 1z j pi over 4, and that's in the y direction. The initial magnitude and phase of the transmitted portion, E0t, is just going to be tau for the TEM mode times the initial magnitude and phase of the incident electric field vector, and that's just going to be 0.588 times ESI, and that's going to give us the result of 23.5 e to the minus j beta 2z a hat x plus 2.35 e to the minus j beta 2z e to the j pi over 4 a hat y. And we could fill in the beta 1 and the beta 2 if we knew what the frequency here was. Omega was redacted in this problem statement, so we can't solve for, we weren't given enough information to solve for the betas here. Just be careful that the beta calculation, it'll give you different answers for the two different media. Frequency stays the same, but beta is material dependent.